So what happens with GMRes in that case? Well, if we recall the relationship between all the matrices involved when you're performing Arnoldi iteration as part of GMRes. Where beta k is just shorthand for. Okay. Oh, I have that H uppercase in the note, should be lowercase. All right. Now, what I'm going to do is I'm going to take the, I can multiply both sides of this by QK transpose. So on the left, I get QK transpose AQK. And then QK transpose QK will be identity, so I'll just have HK over here. And then QK dot product with, oh, it should be a Q. From QK plus 1, that's going to be 0. Because all the columns of QK, the matrix QK, are orthogonal to QK plus 1. So that gets wiped out. So we just have this relationship. So now I'll take the transpose of both sides. So QK transpose A transpose QK, that's just going to be HK transpose. So what it means is if A is symmetric, what does that tell us? HK is symmetric. But HK, no matter what, is an upper Hessenberg matrix.
So it's tridiagonal.
It's tridiagonal. Okay. And so I'm going to call this T sub k from now on. T for tridiagonal as opposed to H for Hessenberg. Okay. So in fact, what this means is Arnoldi, in fact I already made this comment a little while ago, the Arnoldi iteration reduces to the Lanczos iteration, which I discussed way back when I presented conjugate gradient. I presented Lanczos iteration first after sequence descent, and then built conjugate gradient from that. Okay, so now what we can do is we can solve the same least squares problem that beta naught E1 minus TK should be TK tilde YK is a minimum, where TK tilde is defined in the same way as HK tilde. I have TK up top, which is a symmetric tridiagonal matrix, and then I have TK plus 1K EK transpose. So I still have this one row down to bottom, but only has a single non-zero element. So TK tilde is what goes in here. So I still have a K plus 1 by K least squares problem, except at least now the matrix is tridiagonal. So that helps a lot with efficiency. But the thing is, QK plus 1, each new orthonormal vector, only depends on QK and QK minus 1. So the consequence of that is there's no need to restart the iteration. So having that symmetry is huge in terms of efficiency. So that's more like conjugate gradient. Each iteration, well, there's a little more work involved, but actually the main part of the algorithm is matrix vector multiplication. That's order n squared time. This least squares problem is taking more and more time to go from iteration to iteration, but not very much, because the fact that it's tridiagonal makes this system a whole lot easier to solve, having more zero elements. Okay. So this algorithm that I described here from a symmetric case is called min-res. So for minimum residual. So in fact, this method was developed first so for iterative methods for a general symmetric matrix, so where its conjugate gradient could not be applied. So you're solving this least squares problem to compute your iteratives. And then later, the generalized minimum residual method was obtained by fixing min-res in the case where it's not symmetric. So we switched from Lanchos to Arnoldi iteration. Actually, I happen to know one of the inventors of min-res personally, Michael Saunders, who's out of Stanford. Well, he and I had the same thesis advisor, so we're academic brothers. I've always felt. Yeah, he's a good 25 years old than I am. Okay. So min-res and GM-res are two very commonly used iterative methods for moving beyond a case where A is symmetric positive definite. And both GM-res and min-res are implemented in MATLAB. Okay. So questions about either of these methods? So these two methods are part of a larger class of Krylov subspace methods. They all work by working with Krylov subspace. It starts with your right-hand side, B, and keep multiplying it by A. So basically what you're doing is you're approximating A inverse B by approximating the inverse using a polynomial in A. That polynomial is determined by Lanchos or Arnoldi iteration as appropriate. Okay. So this is one way of generalizing conjugate gradient in these cases. But there's, but the thing is, suppose we're dealing with a general matrix, so not even symmetric. So we're stuck with GM-res, that's all we know about right now, these non-stationary methods. And you have to put up with the fact that there's more and more expense for iteration, and you have to figure out how often to restart and so forth. Is there any way that we can generate these vectors, these cubes, using a short recurrence relation, right, like before, where each one depends on the previous two? So it is possible to do that, but as with other things, you have to make some concessions. And unfortunately, I'm running low on time.
So the expense just comes from the grams per minute?
That's the main part of the expense.
Yeah, and then you have the...
So this matrix vector multiply.
Okay.
Yeah, this gets pretty significant after a while.
Okay.
Another problem you could have is, another reason for restarting, is these vectors, these q's, are supposed to be orthogonal, but it is possible to have some loss of orthogonality among those vectors. So you have an accumulation of Randolph error. So not only are you having to incur more expense in solving this least squares problem, you're losing accuracy as you go. Okay. Let's see. 6, 7, 8. I'm at a natural stopping point. Yeah. Okay, so next time we'll do biconjugate gradient, which is another course for general unsymmetric matrices. Well, since we've still a few minutes before I have to go, anyone who has any homework questions is welcome to ask them.
Okay.